So, in the previous lecture, we started considering the quantum effects on phonons, but I'll remind you a bit where our conclusions about phonons. Okay, our main conclusions were that if you have a d-dimensional crystal, you have d acoustical waves or mode, p minus 1, where p is the number of atoms in a unit cell. What signifies optical modes? Those are modes that the dispersion relation when k goes to 0, meaning very small length scale, go to a finite value of omega, and the optical modes follow or for small k's, where this just signifies velocity of this acoustical wave. Okay, all that we treated. How to get the lambda s if we know to write the interactions we're supposed to know. But this is the main features that we have studied about phonons. Okay, then we said, okay, the heat capacitance from the classical point of view, write it this way. Why? Because the energy is n times 3 kBT, and the heat capacitance is the derivative of the energy. And we have half kBT per degree of freedom. We have 6 degrees of freedom for each atom in our usual 3-dimensional world. That's all. Then we said, well, for very low temperatures, this is not necessarily true. Why? Actually, it's twofold. The first reason is basically that the phonons have a quantized energy. We wrote it down. And since this is a discrete behavior, for very small energies, not all of these phonons can take part in the game. Some of them are completely forbidden from the beginning. These are the optical modes. Because they have a finite omega for whatever k you choose. But even for the acoustical phonons, it depends on the behavior. And that's what we're going to do in this lecture, see how it depends. Okay, perhaps before I'm going into the calculation, I want a few words about, well, we said phonons and we said a particle, right? And if I'm looking only on the energy, you can say it's very similar to the energy of a photon, right? That you should remember from statistical mechanics or modern physics. Okay, so are photons and phonons both particles? What defines a particle? Any ideas?
Phonon is a quasi-particle, right? It's not something that is actually a particle, but it can act over other particles as a particle.
I would prefer not to introduce at the moment the word quasi. I'll use a different word. I would say that the phonon is not an elementary particle. Okay? Photons, we don't know on any mechanism that lies beneath it. Well, if you go back and read Maxwell's writing, not that I recommend it necessarily because it's very, very thick and hard to understand. When he came to explain what is an electric field, he actually put a mechanical model below it. You have some ether that has all kinds of interactions within it, and the photons emerge, or the electromagnetic waves, he didn't use the word photon then, as a result of modes in this substrate. Since Einstein we threw out the substrate, no one believes that there is any mechanical structure below it. For phonons, we know exactly what is a mechanical substrate below it. It's these atoms with interactions between them. So, in a hand-waving way, if we don't know any structure below the particle we're discussing, we call it an elementary particle. If we know what is a substrate on which these particles emerge from, we call it just a particle, not elementary.
But for example, protons and neutrons that have quarks within?
Well, nowadays, no one calls a proton and a neutron an elementary particle. In the 20s and 30s, people thought that they are elementary particles. Now you can come and say, excuse me?
They even thought that until they find it, because then when they try to apply the same methods of finding for electrodynamics, they saw that the measurements don't make sense.
Well, there were reasons also before World War II. A bunch of physicists, Heisenberg for example, didn't think that they are elementary particles, but he couldn't any formulations that he came up with diverged. Feynman found a solution to this divergence. Partially. Okay, but anyway, at the end of the day, for any type of particle, doesn't matter if it's elementary or not, we have some field, in this case a field composed of masses and springs. For the electron, we just write down the field without really believing that there is something below it. And the excitations of this field, the quantized energies, are the particles. Why do we call it a particle? Because in this case, we can have 0, 1, 2, 3, 4, a quantized number of excitations. Very naturally, we call it particles. Does anyone ensure us that for what we are calling nowadays an elementary particle necessarily there is nothing below it? We don't know. So basically, if I'm looking on the behavior of the phonon, it behaves very similar to a photon. The only difference is that you know exactly what is the classical model that stands behind it. For the electron, you write a model, you don't know what is the physical substrate that it exists on. Okay, what type of particle is this phonon? A boson. Why? Because I told you that it could have 0, 1, 2, and so on. That comes also out of the quantization of the field. We didn't put it by hand. That's the results that we got out of the calculation, and in the graduate course you'll see exactly how you get to this point that it's a boson. Okay, so basically, let's stop a minute about the S. What does that S tell me? Basically, that I have different types of phonons which have different dispersion relation. Each one of them behaves like a boson, but they are different. They have a different dispersion relation. So let's say in a simple cubic three-dimensional system, we have 3 types of phonons. Or they are called sometimes branches. What signifies the difference? CS, which is not necessarily the same. Could be, but it's not necessarily. Okay. So, what I have to do here in order to calculate CV, the heat capacitance. Oh, just one more thing. We sometimes write CV, the heat capacitance per unit volume, writing it down as small c, or the energy per unit volume. So it's the same divided by the volume. If I want, I can write density here, because n divided by volume is density.
You have to plug it into the partition function. You have to calculate the partition function.
I'm missing the value of nks. Right? Once I know it, it becomes just mathematics. So, One way around it is to write down the free energy. As I told you numerous times in this course, part of the fun, part of the problems with this course is we're pulling concepts from all your previous studies. Okay. You know this guy, the summation here. What is it?
The geometric.
Z in the language of statistical mechanics, just the sum over all energies. And beta, right, 1 over kBt. So why is it true even that we don't remember our course in statistical mechanics?
See that when you derive V, you get the E. Also.
Right, if you do a derivative over beta, you get EI times. So it's a weighted weighted average over the energy. Okay, so it makes sense. Minus just to kill the minus. Okay, let's write down F explicitly. What did I do here?
You just use the fact that the energy is additive. You expand it, and that's the multiplication of exponent.
Look what's written here. This is an important step, therefore I do, which appears in many subjects, therefore I'll do it a bit more carefully. What's written here, really?
It's
I have here instead of I, I'm summing over K and S, right? All energies. When I'm writing down what's happening here, what is this contribution? What is EI? What is the state of this?
It's the energy of some state.
It's AE to the H bar omega times MKS plus half.
We are talking here about an energy of the whole system, right? Not of a specific phonon.
Yeah, but
So how do I write down the energy of a specific state?
It's over there.
I have here a sum of KS's. For each state, I have to write down the energy of the state, or the dispersion relation if you want, and what else? How do I enumerate, give a meaning to the state?
MKS.
I'm taking all the NKs that I have and just write a list. A state of the system is, let's say, for NK equals 0, for the first one I have 1 phonon, for the second one I have 3, for the third one I have 0. That signifies the state of the system. Therefore, what I really have here is a summation over all these guys that go into exponent. But if I have a summation over all these guys, instead of writing it down as e to the minus b sigma ks h bar omega s k nks plus half, I can write down for each k of s a multiplication of the exponent, right?
Instead of for each KS, you do the total NKSs for all states.
And then write down the total NKSs. So I have a multiplication over all KSs. Perhaps I'll write down another step. And so on and so forth for all k's and for all s's. So this is a multiplication. So this is what's written here. On a multiplication of all ks. Here I just once put in 0, once put in 1, 2, 3, 4, 5. So each term here has a multiplication of an exponent and the specific state of the mode, how many phonons sit in this mode. So this is what's written here. You have learned it in statistical mechanics, but for some reason each year when I come to teach it, no one seems to understand, therefore I took this 5 minutes to explain it. Okay, so until here everything's good.
Now you can take out the multiplication.
Now I can sum up just a geometrical series.
Yeah, but also you can say you can take out the multiplication from.
Yes, then I'll use the line. Let's do it one step at
I
a
remember how we would do that trick. We were like, well, this is the multiplication. We can't solve the multiplication series I'm going to solve, so we'll just take the line of it, and then we'll just afterwards do the utility how we get.
well, the reason for the line is deeper at the end.
Yes, here it
The
is. I
deep-
remember mechanics we would sometimes get problems where you would have to solve, it would ask us to solve the multiplication, but we couldn't, so we would solve the summation of.
Well, go back to the end of the Middle Ages. You had somebody, I think it was Nepel, an English mathematician, published a logarithmic table.
Oh yeah, that's
Why did he do it?
because no one had calculators.
Right, they didn't know how to multiply, so it was easier if you have a multiplication of two numbers, read off from the table the values of the log of these numbers, sum them up because summation is easier, look in the inverse table what's the result, and suddenly you could.
Especially for larger numbers, summation is easier for larger numbers and it's less likely to be a mistake.
Right, so suddenly all kinds of traders all over the world started using logarithmics to do their bookkeeping, and artillery officers all over the world, instead of multiplying things that they had to multiply some sign times velocity, they went and used these logarithmic tables because logarithmics is an easier way to do multiplication. That's all that's behind it. Nowadays, where you have computers, no one remembers this point. But logarithms were introduced in order to simplify multiplication. Okay. Okay, so I'm removing this. A0 in the language of the series, and this is Q. Up here A0 times 1 times A0Q, A plus A0Q squared, just the summation over a geometric series. High school, nothing beyond that. Okay, now we get to the point of exchanging this ln of a multiplication by a summation. No, I'm using this as something that multiplies all of them, right? Geometric
I see,
series A0 plus A0 cube plus A0 q squared. So that's the half, the e exponent to the power of half is just
Right.
a constant that multiplies all of them.
Right.
I already wrote it, I'll finish it. That's all we did. Performs the derivative.
With the line, right?
No.
Behind.
Okay, so, sorry, line here.
Right.
Of course. Perform the derivative and end up with so u is minus dou f. So we arrived at something we already know. This is the probability of occupation of a state n for bosons. Okay. So we started from heat capacitance. The change in the energy as we change the temperature.
what happened to the V1 over V? The method up for you. Up for minus the derivative of f rho.
I wrote down large U. What happened to the plus half term?
It's a derivative.
So, doesn't depend on t, I don't care. Okay. Now we get to something that creeps us up on us whenever we do physics. We used some prescription to calculate something, and we got something that is not easy to calculate. The summation is not trivial. So we pull out our bags of tricks and try to do all kinds of manipulations on it. One of the first things that you always should get used to doing is look at the limits. Large t's, small t's. Why? Because first of all, it almost always simplifies the mathematics. Second, usually at the limits you have some physical intuition about what should be the behavior. So if you have physical intuition about what the behavior should be, you can compare to your result and decide, did you make a mistake? Perhaps your intuition was wrong, but you have at least something to compare the result to. In, let's say, Moed Bet of the quantum mechanics course, I gave people a combination of 0, 1, and 2 state of a harmonic oscillator. Ask what's the energy. If someone got an energy higher than the second state, should have put a red flag that something is wrong, even without knowing nothing about how to do the calculation. And same here. Let's start with the classical limit, large t. What do I expect the result? It's written here. So let's do it. Keep our notation in order. Should pay attention. I did hear something slightly not consistent. For the optical modes, no problem at all. Can always... Oh, sorry. I just have to, if you want to sum up all the modes, the only thing you have to take into account is the omega of the highest optical mode. Once you're above it, you're okay. If you're in between, you can have a region where you're perhaps much larger than the acoustical modes, but lower than the optical modes. But let's assume here temperature is above any value of omega that can appear in this system.
The density of states between optical and acoustic modes should vary, right? Shouldn't be the same because we have information.
Well, we didn't define yet what is density of states, but the simple answer is the number of states you know by the number of modes, right? And per k, you know exactly. Now, we will discuss density of states when we talk about electrons, but here you don't even need it. You have definite k's, and for each k you have p times d states, right? Usually also for electrons, density of states, if you are discussing k vector, is no problem at all. The problem is starting when your density of states per energy, and energy is proportional to k squared. So it becomes messy. Here it's right, with the same k. Right. Okay, so the guy in this expression which ruins our day is a 1 over ex minus 1. But now I explicitly said that x is small. Okay, I just expanded it in a series. Pulled out power of x. Now I'm left only with x, so I'm pulling out the x, and I have 1 minus half x, 1 plus half x, and to the power minus 1 I get a minus. Okay, so can write down the summation I have to perform. Consistent, I write them third term. What did I do here? Nothing except writing down x, which is beta times h bar omega, and remembering that beta is 1 over kbt. Simple algebra method. Here. Okay. Derivative falls off, constant. Performs a derivative. Derivative of this guy is kb. Can pull it before the summation. So it's a summation over 1. This guy becomes minus 1t squared. Again, I pulled out the constants before, but here I can't pull the omega because omega does depend on k and s. So what did we get here?
When t is large, then we're left with
We just have to finish up this summation, which is simply the number of k's and s depends on the number of atoms times dimensionality. If it happens to be 3, so it's 3n. Back, I've already erased. This is the classical result, and we have here some correction that comes out of the dispersion relation. So even at high temperatures, we have some correction. Unless it's extremely high, where 1 over t squared is so small that we can forget about it. The opposite limit Okay, so let's stop a minute and look on what's written here. Okay, the summation is over discrete values of omega, which is very small compared to 1 over t here. That you go from some discrete k to the next one, to the next one, to the next one. So, what can I do to simplify my life? Excuse me?
The negative one. It's irrelevant.
Well, that also, but summations are always hard, integrals are easier.
I mean, I can't figure out how you can turn them from
Excuse me?
you would still need a summation for the different s's then.
I'll leave the summation on the different s's. Right. So how do I write it? Well, simple. CV. S is of order 3 or 3 times p minus 1. It's a finite number. So I can do a few integrals with different values of s. It's easier than do an infinite.
Can't do,
Okay. A bit more of a simplification. The contribution from optical branches is equal to 0. Why? Because I'm dividing here a finite number by something that is very small. So this 1 over exponent is a very small contribution. I forget it.
Shouldn't we put the integral need the density of states?
Wait a minute, we'll. Since most contribution comes from small values of omega, where we had this linear relation, instead of writing we can write constant velocity approximation of the dispersion relation. Okay, so what did I do here? anywhere that we had omega sk, I wrote down this linear relation. So it's here and here. And instead of integral on vector k, I wrote down unit of volume in polar coordinates. It's very good coordinates. Okay, instead of I'll just write down what's special about x.
It just makes it easier.
It has something more though, which is important anywhere where you have to do integrals in physics. What are the units of x?
It's dimensionless.
It's dimensionless. Therefore, even if I won't be able to perform the integral, I will know that my t dependence is out of the integral, and I will be able to perform the derivative on it. Okay. So already at this point, I know that the dependence will be t to the third of the heat capacitance. Whatever the number that comes out here, it's still a number. In this case, we can't even perform the integral, so life is good. But in any case, it's just a number. The functional dependence on t, I already know without performing this integral. It's t to the third. What does that mean? As t goes to 0, what is the contribution? What is the heat capacitance? Yep. Can't hear it.
T to the third.
So if t goes to 0, so it's 0. A complete different answer than we would have gotten from the calculation of the classical behavior. It's not a constant, it's 0. Why? It's clear, because as t goes to 0, you can't supply enough quantas to move phonons. Heat capacity tells you I'm at a given temperature, how many quantas of h bar omega can I fill with this amount of t? But t is much smaller than h bar omega. You can't. So not only you can't, you know exactly what is the dependence on t. Okay, another interesting point. What is the dependence here on the branch, on S?
We will need an...
It comes in only here.
And the sum.
No, the sum is just adding, let's say 3 times for a 3-dimensional system, some different number here. But this is the same, everything else is the same. So you're basically just averaging over CS. Strange average over 1 over CS to the third, but still an average.
But we don't have an explicit expression for CS, right?
It's a number. If give me from the previous lecture D, and I'll be able to tell you what CS is, right? Depends on the lattice. Well, to be more precise, I should have written it here because it can have an angular dependence. So I'll write it this way and define let's perform this integral. I'm doing it just because it has, as I said, it's a number, but it has a nice trick to obtain this number. repacked it into the series representation. This integral I know to perform. Why is that? Someone can tell me how to perform it?
Just the gamma function.
It's complicated for me. An easier way.
Just the gamma function.
Okay, so actually I'll write it here. It's a gamma function, but not everyone knows what's a gamma function. And it's actually so a digression to basic mathematics. This thing we know how to perform, right? Hope so. Okay? You should remember how to do an integral of an exponent. Now, what is this guy?
That one.
Each time that I do a derivative by n, I pull down one x, actually a minus x. So minus x plus x minus x, so I have to put here is the integral that I'm interested in. Okay, but I did this integral, so this integral is also equal minus right? So first I pulled down here minus 1, minus 2, and minus 3, right? So it's 1 over 6, 1 to the fourth. I believe it's simpler than doing integration by parts or something like that. You'll see this trick a lot in field theory. Every time that you have an exponent to the power of x to some power times an exponent, this is the way to go. You'll also spend half a lecture on having more complicated structures here. And the amazing thing is, if you have a vector times a matrix times a vector, this is a number, right? That's how you're calculating energy in quantum mechanics. So you can also write an easy way to pull out all powers that multiply it. It's used ubiquitously a lot. Okay, so life's good. sorry, 6 times. Comes out, not 1 over 6, 6. Sorry. Okay. What do I do with this? Well, this is a summation that we know to perform. I won't do. To perform this, someone has an idea what we do.
The Fourier series and Parseval's theorem.
Tonight is the simpler way.
We use the Euler formula, right?
This is the Euler formula, but how do you get it? Integration in the complex plane. You use these guys as poles, write down a trajectory in the complex plane, do it. You should have taken the course on complex analysis. That's one of the famous examples there. Perform, and what you get here is pi to the 4th divided by 90 times 6. So it's pi to the 4th divided by 15. Actually, if you think about it, this is mind-boggling, this relation. Why? They have here only integers, right? Each term and term is just a well-behaved integer. What the hell do I end up with pi to the 4th from the summation? Joys of mathematics. But anyway, for our problem, as I said, this is a number. It doesn't change dramatically. Well, it doesn't change at all my t to the 4th conclusion. It just multiplies this by these numbers, and that's that. So if I couldn't do it, I could only go to a computer and do it numerically, it wouldn't have really changed my physical understanding. But it's still always nice to see it in a closed analytic form. So as I pointed out, for t goes to 0, we have 0 heat capacitance. The system just can't receive energy at very low temperatures, just can't swallow it. Okay, for completeness, I'll say something about intermediate temperatures. The important thing is just setting here an energy scale that helps us characterize materials. The calculation itself, the good old days when you didn't have computers, was somewhat helpful. Nowadays, you can go and stick the sum into a computer and get a result. No need to sweat hard and write something for intermediate values because the physics we pulled out at the post in the two limits. Okay, so this is the Bayes temperature. Bayes was an experimentalist in Berlin who did some measurements about heat capacity and wanted some extrapolation between T goes to 0 and large T's. So what were his assumptions to simplify the calculation? Assume you have three acoustical branches. He lives in a three-dimensional world, makes sense. As we saw, the exact value of C goes into some averaging of the C's. So for him, take all the C's equal. So you have three branches with the same dispersion relation. What happens to the optical modes? Still, even in intermediate temperatures, their contribution is relatively small. Because as we can see, the acoustical branches have much more states that can get and emit this energy, KT, than the optical modes. So ignores them.
Why are they called optical modes?
Okay. Think a moment and answer.
They emit light. They are excited by light.
The usual way that you cause an acoustical wave to resonate, to absorb energy, is by changing a bit the position. I'm moving some of the atoms on the tabletop and that spreads out. Right? But then basically what I see is it's much easier for that to spread if each atom in the next layer gets a bit of more movement. How do I take two atoms, let's say, and cause them to vibrate in the opposite direction at very short length scale? The only way is to send some particles there that will have a collision around one or two atoms and cause this vibration. A photon is a lovely device to get that. So that's why they're called optical branches, because they are easily excited by photons with the correct frequency. not so much by a mechanical force. The mechanical force will work all around, it will spread all around, you'll have relatively long wave lengths. Not what you want for the optical modes. Okay. Second, how do I populate these modes? So his answer was, well, I'm filling them up till some k, they're zero above it. What does he gain by that? Basically, that he can't put a cutoff. So where will be the cutoff? And that's the main insight into the Debye temperature. What did I do here? I took a sphere of radius kd, asked how many states are there, and populated them according to the number of atoms that are in the game. So I fill up all the modes till kd, and the total sum of modes should be equal to n. Okay, this leads to where small n is n divided by v. Okay, kd is a 1 over length scale. How do I translate it into a temperature? The dispersion relation gives me a connection between omega and c, and k, sorry. And what do I need? The temperature, so I need h bar. So And this scale tells you when you're crossing over from quantum behavior to classical light behavior. For most materials, it's around 100 or a few hundred Kelvin. So it means that in room temperature, most lattices behave classically. In lower temperature, which are still achievable in laboratories, it's already showing quantum behavior. Okay, so we'll stop here, and the last thing that we want to see, consider about phonons would be how can we see an individual phonon? That would be by scattering with another particle, which could be a neutron, could be a photon. We'll consider both cases.
Electrons also, right?
Yes, but we don't like to use electrons. Can you give me a physical reason?
Charge.
Hmm?
Maybe the charge.
Not maybe, it is a charge. In order to go into a lattice, you don't want a particle with charge that will scatter off all the ions and electrons in it. You want something that's neutral. Photons or neutrons. Each one has its own advantages and disadvantages. Study. Neutrons, the problem is you need a large facility to get it.